Okay, so do you remember that I said that matrices have lots and lots and lots of uses in the real world? Because at the moment you're probably looking at this going, I can't really see the point of doing it. Like, it's quite long, it's quite laborious. Why are we interested? Well, number one, the way which matrices can be used, okay, they're literally used every single day when you're on your social media. Okay, so the way which social media algorithms work is using matrices to understand connections between people. And then they can understand things like weighting of nodes, so weighting of people to see who's the most popular. And then they can sort of look at your viewing habits and kind of try and follow the networks through. Using matrix algebra, they're able to work out, I think you might like to follow this person, or I think you might like to connect with this person. Okay. Another place where matrices are used, sort of quite famously, Google. Okay, so the way which Google literally works is using a page rank algorithm, which is basically matrices. Okay, so they're really, really useful in the world which you're using, so the technology world that you're used to, but you didn't even know about it. So matrices are really useful there. Okay, another place where matrices are really useful is from the perspective of graphics. So that's the sort of things on your screens, you know, your phone screens, how animations move. Sorry? Resolution? Yeah, resolution, absolutely. Image, CGI, it's all done with matrices, okay? So lots of things going on in the background. And I thought I'd just give you a little bit of a taster of how it could be used, okay? So you can see on the screen here, I've got two vectors. So you've got my coordinate grid, so I've got my y-axis and my x-axis. And I've started at the origin, so I put the origin in blue down here. Okay. And then from here, I've got a blue arrow, which I've called A1, and then a red arrow, which I've called A2. Okay. And then from that, I've formed a matrix A. So can you see that the vector A1 is 1, 0, because it's one step across and no steps up. Okay. So remember when we did vectors on Monday? Okay. Just simply a movement from one point to another. It's 1 across and 0 up. And you can see that I've put that vector in the first column of this matrix. Okay. And then A2, I've put, which is the red one, I've put in the second column of this matrix. So the red vector is 0, 1, and I've just literally written that in the second column. Does that make sense? So this matrix up here, the blue vector corresponds to the first column, and the red vector corresponds to the second column. Okay? And what this means is that I can literally update it live. So say, for example, I wanted to change A1, instead of it being 1, 0, to be 2, 0. I can literally just drag and drop this point to 2, 0, and you see it change in my matrix.
Is this GeoGebra?
GeoGebra, absolutely. And this is available on my GeoGebra page, Maths Partner, so you can go and play around with it if you want. Okay. And likewise, if I update A2, maybe make it a bit more adventurous, move it to 1, 1, you can see that that gets updated in my my matrix. Okay. So literally, this matrix is built from movements of A1 and A2. Now, if I just take this back to 1, 0 and 1, 1 again, so what I had at the beginning, what I can do is I can create a shape from this. So this is my shape which I'm going to use. Okay, it's going to be a square, and you can see I've got 4 coordinates. I've got P, Q, R, and S. Okay, so the coordinates of P would be 1, 2. You can see that the coordinates of P, 1, 2, I can think about it almost like a vector, is in the first column of my matrix. Does that make sense? Yeah? And then Q would be 1, 1. Happy with that? And that's in the second column of my coordinate matrix on there on the right-hand side. Okay? And then you can see R would be 2, 1. That's in the third column of my coordinate matrix. And S is 2, 2. So that's in the fourth column of my coordinate matrix. So essentially, this shape, P, Q, R, and S, is the same as this matrix here, where the columns correspond to a different coordinate. Does that make sense? Now, if I multiply these two matrices together, you can do it by hand if you want, okay? But this is the result on the right-hand side, okay? So this is my matrix, which remember is built by my blue vector and my red vector. I take my coordinate matrix, and then I multiply those two things together, and then the result is over here. Now you might go, well, okay, fine, but what's actually going on here? Well, at the moment, not a lot, but look what happens if I change my blue and red vector. So for example, look what happens if I change my blue vector to be at 2, 0 instead of at 1, 0. Okay? My shape changes. Now what I'm literally doing, just to recap, is taking this vector and multiplying it by this vector. So my vectors, which are defined by blue and red, okay, is my first matrix, and then my coordinate matrix multiply them together, and I get this matrix. What do you think the matrix on the right-hand side corresponds to?
The area?
Not the area. Not yet, anyway.
The coordinates?
Of
the new shape?
Of the new shape, absolutely. So what I can literally do here is just by fiddling around with different vectors of A1 and A2, I can make a transformation of the original shape and I can see where the new shape is without even having to draw it. Okay? So for example, let's suppose, oops, let's bring that back, okay? Let me hide the shape because it's getting a little bit confusing. Let's suppose I want to perform a rotation of 90 degrees anti-clockwise about the origin. So let's think, if I perform a rotation of 90 degrees anti-clockwise about the origin, would you be happy that the red vector ends up at -1, 0?
Yes.
Okay, and would you be happy that the blue vector ends up at 0, 1?
Yes.
Okay, now I can see what happens if I show my shape of what happens if I rotate this shape 90 degrees anti-clockwise around the origin. I've literally just taken this vector, which is my transformation matrix if you like, and multiplied it by the coordinate matrix, and I get the new matrix out, which are the new coordinates of my shape. I can even do things like stretches. So let's suppose now I want to stretch it by 2 in the vertical direction. Can you see that just simply by changing this first matrix, by thinking about my original vectors, what would happen with my original vectors, I can see where my new shape is going to end up. Is that okay? Is that clear? Okay. Now it used to be on the syllabus that you had to understand all of these different transformations. You no longer have to. So if you have a look at question 5, okay, so question 5a and 5b, I've got loads of transformations in there. Okay. You don't have to worry about those anymore. You used to, but you don't have to worry about them anymore. Okay. But you do need to understand the concept of question 6. So think about what's happening here. Think about what's happening here. In fact, let me just stretch that vector out a little bit more. If I want to not know what's happening with my transformation, but if I want to know how many times bigger my new shape is compared to my old shape. So I want to find out how many times my area has been increased by this transformation. I can do that really easily. So have a look. I started off with a shape which had an area of 1. That was my old shape. Okay? And once I'd performed this transformation, so once I'd taken this transformation matrix, multiplied by my old coordinate matrix, and got my new coordinate matrix, I find that my new shape has an area of 2. Now my question is, could I work that out just simply from the transformation matrix? And the answer is yes.
Yeah, just multiply it.
Multiply what?
The matrices.
Oh, you could, and then you could draw it out and find the resulting shape. But actually just looking at this matrix here, so actually if I hide the shape, okay, if I hide the shapes, look at that matrix there. Could I know that whatever shape I started with, my new shape will be twice as big? Just purely from this matrix here.
Twice as big?
Yeah. And you can really easily. It's using the cross technique. Now this is something called a determinant, and I'll talk you through it on the board in just a second once I flip the camera around. Okay? All I do is I take the leading diagonal, which is this, the 0 and the 0, multiply them together. So 0 times 0. Then I take away the product of the non-leading diagonal, so -1 times 2. So just check, what's 0 times 0?
0.
Then I take away -1 times 2.
2.
So negative, take away -2, I end up with 2. And lo and behold, my new area should be twice as big. Does that make sense?
It does.
Okay, so what if now I wanted to do a weird and funky transformation? So for example, let's move this one down to, I don't know, about here. Let's get that right. About there, okay? What if I wanted to know that still my transformation was going to cause my new shape to be twice as big? Let's just check. What's 0 times -1?
0.
Okay, what's -1 times 2? 2. -2, take them away, you end up with 2. Okay? Now, is it possible for the determinant to come out negative? Yes, it is. Okay? And you can do that just simply by thinking about something like this. Okay, so hang on a minute, let me get this right. let's do something like that. Okay.
Still not 0.
Sorry, wait. Okay, let's think about this. Okay. What would the determinant of my matrix be? So -1 times 1.
The negative 1.
Negative 1. Take away 1 times 0.
0.
0. So you end up with -1. Okay? Now that means that my new shape will still have an area of 1. It will just be it's flipped as well. So my new shape will be flipped. Okay? So if the determinant is negative, it means that there's been a flip going on. And you can see that because with my old shape, the P and the Q were on the left-hand side. With my new shape, the P and the Q are on the right-hand side. Yeah? And the S and the R are on the right-hand side with my old shape, and S and R on the left-hand side with my new shape. So there's also been a flip going on. So if it comes out as negative, don't worry, it just means that there's been a flip which has happened. Okay? But the area will still be increased. Now here's a question. Is it possible for my area to come out as 0?
Yes.
Good. You could have, for example, something like this. But let me bring that down a little bit more. Something like that.
When the points are equal to each other.
Yeah, good. So literally what's happening here is my old shape, my black shape, is being projected onto a straight line. And you can check that out. So 1, 1, 1, 1, okay? If I multiply by my coordinate matrix, the points get projected to a straight line, which means that the area is going to be 0. Okay, and you can check that. What's 1 times 1?
1.
Take away 1 times 1.
1. So 1 minus 1 equals 0.
1 minus 1 equals 0, absolutely. Okay, so if the determinant comes out as 0, just think my shape gets projected onto a straight line. Now, one final thing which you need to be aware of, and then I'll talk you through it on the board. One final thing you need to be aware of is the idea of an inverse. So if I take, for example, back to here, okay, an inverse matrix was simply a way of getting from the new shape back to the old shape. So I'll say that again. An inverse matrix is simply a way of getting from my new shape back to my original shape. Is that okay? So transformation matrix takes my new shape to my old shape to a new shape. An inverse matrix does it the other way. It takes my new shape back to my old shape. Okay. Now I'll talk you through how to find the inverse in due course, probably next week. Okay. But there's one case where an inverse doesn't exist, and it's this case. When your new shape is projected to a dimension lower, in other words, in this case to a straight line, you can't get back to your old shape. So there's no inverse which exists. There's no way of getting from here back to here, because there's an infinite number of possibilities of what your old shape could have been. Does that make sense? Yeah? So 3 key ideas. A determinant tells you how many times bigger your new shape is compared to your old shape. Okay? If your determinant is negative, it just means that there's been a reflection which has happened as well. If your determinant is 0, it just means that your new shape is just a straight line. And if you have a determinant of 0, an inverse matrix will take you back to your new shape, so your old shape, from your new shape to your old shape. If your determinant is 0, it just means there's no way of getting back. Is that okay? Okay, so I just wanted to draw your attention to that on the board because I think it's quite a nice visual thing. All you really need to know, so you don't need to know all that information, all you need to know is how to actually calculate the determinant. So this is the last thing, and then we'll finish off. Okay, so how do you calculate the determinant? Nice and easy. So let's, for example, take the first one. You've got -1, 0, 0, and 1. Okay, how do you calculate the determinant? Simply multiply those two things together and take away those two things multiplied together. So it's going to be -1 times 1, take away 0 times 0. Okay.
Is that specific rule going to be in the exam?
Yes, that is in the formula sheet. So in general, if you have a matrix that looks like this, A, B, C, D, that's your matrix, okay? That implies that the determinant of that matrix will be A times D minus B times C. That's it. Okay? And just be aware, all determinant tells you is how many times bigger your new shape is going to be compared to your old shape. That's it.